In this video, I want to go over another example how to take an inverse Laplace transform without using partial fraction expansion. So all I'm going to be doing is looking at my Laplace transform table. I'm going to be manipulating the expression that you see here, the 3s plus 7 divided by 4s squared plus 24s plus 136 to fit my tables, and algebraically manipulating this, and then taking my inverse Laplace transform. So right away, the first thing I see is I'm going to have to manipulate this denominator. The first thing I'm going to do is I'm just going to take out a 4. So 1/4 times 3s plus 7 divided by s squared plus 6s plus 34. Now, I'm going to still have to work with the denominator. None of my tables are going to have this particular form. I need to figure out if I have real roots, if I have imaginary roots. Now, the way I can do that is I can look at part of the quadratic formula, specifically the square root. If I look at the square root of b squared minus 4ac and remind myself what the quadratic formula is, ax squared plus bx plus c. So a is equal to 1, b is equal to 6, c is equal to 34. If I put that into this expression right here, I get 6 squared minus 4 times 34 times 1. I don't even need to compute this. I know that this is going to come out to be a negative number. That negative number means it's imaginary. And I'm not going to be able to just analytically just break up this term into two polynomials. Or I'm going to have to complete the square. So I'm going to have to say this is equal to 1/4 times 3s plus 7 divided by, now we need to complete the square. And to complete the square, we're going to group terms in a specific way. So I'm going to have this is s squared plus 6s. Now, what we're going to do is whatever value we use here for the coefficient of s, we're going to divide it by 2. We're going to add in 6 divided by 2, and we're going to square it. And then we're going to group all of these terms together. They're just going to stay together. Then we're going to work with the rest. So I'm going to have this plus 34. And because I added in a 6 divided by 2 squared, I'm going to have to subtract out a 6 over 2 squared. And that's so I'm not changing this equation. Now, what is 6 over 2? 6 over 2 squared is 3 squared. So it's equal to 9. So we can say this right here is s plus s squared plus 6s plus 9. This right here is equal to 25. And I can further break this down. I can say this is s plus 3 squared. So now I've completed the square, and let me rewrite this just a little bit nicer. So this is going to be equal to 1/4 times 3s plus 7 divided by s plus 3 squared plus 25. Now let's go and let's look at the tables, and I've done this, and I've picked out two entries that look like they will be useful. And they have this s plus a squared term, and they have a b squared term. Well, we can easily make this a squared term. 25 is just equal to 5 squared. So now our denominators are of this form. We need to do something with this numerator right here. Now, I'm going to start with this second table entry because I see there's an s term. The first one doesn't have an s term. So maybe if I get lucky, I'll be able to get it into this form very easily. So first, let's write this 1/4 times, what do I need to do here? Well, I can take a 3 out. So if I take a 3 out, then that's equal to s plus 7 over 3 divided by s plus 3 squared plus 5 squared. Okay, so we're a little bit closer, but there's something we need to be careful. We can't just say, okay, this is good, because those two values need to be the same. I have an a here and an a here. So I need to get this to be equal to 3. Now, how do I do that? Well, what I can do, let's write the 3/4 times s plus 7/3 over s plus 3 squared plus 5 squared. What I can do is in this numerator, let me add 3 and let me subtract 3. That doesn't change it. And let me regroup these differently. Let me regroup this as 3/4 times s plus 3 plus 7 over 3 minus 3. Now, 7 over 3 minus 3, 3 is equal to 9 over 3. So 7 over 3 minus 9 over 3 is equal to minus 2/3. And my denominator hasn't changed. So my denominator is still s plus 3 squared plus 5 squared. I know I write my 2's in 2 different ways, but all right. So now let's rewrite this again. So 3/4 times s plus 3 minus 2/3 over s plus 3 squared plus 5 squared. Now, what happens here? Well, I can split this up into, I can't use this yet. Not yet. But I can split this up into 2 different terms. So when I split this up into 2 different terms, I get this is equal to 3/4 times s plus 3 divided by s plus 3 squared plus 5 squared minus 2 over 3 times s plus 3 squared plus 5 squared. And okay, so now this is real good. This term is exactly like the bottom entry right over here. It's exactly like that. My a's are the same. My denominator's in the right form. So this first term, right away, I can say this is going to be e to the minus 3t times the cosine of 5t. And don't forget this 3/4. So I have 3/4 times that. Okay. Now we need to work on this second term. So I'm just going to sort of isolate the second term right here. So this is not equals, but so the second term is going to be 2 over 3 times s plus 3 squared plus 5 squared. What can I do? Well, just like I need to add in a term. So if I look at this, I have a b term and I have a b squared term. So I need to get this top term. This needs to be equal to a 5 for me to work with this equation or this entry. So what if I multiply this by 5 over 5? That I'm multiplying it by 1. And what if I factor out this 2/3? So instead of 2/3, I just factor out, right? I take the 2/3 out of that equation. So I have 1, and then I have 2/3 times that. Okay? So now I can rewrite this as 2/3 times 1/5 times 5 over s plus 3 squared plus 5 squared. And yeah. So now let's work on this second term a little bit more. And I really, if I remember correctly, I have this 3/4 term. So really this is being multiplied by 3/4. This is being multiplied by 3/4. So when I multiply everything through, that 3 is going to cancel. This 2 and that 4 is going to be a 1/2. So this is going to be equal to 1/10 times 5 over s plus 3 squared plus 5 squared. Okay, now this is good. I have this is the same as this. Now I just got to pay attention. It's a minus. So I'm going to have minus a 1/10. I've already multiplied that 3/4 through. And this is going to be times e to the minus 3t sine of 5t. So this is my inverse Laplace transform of this x of s that I have right here. So this is my answer. Hopefully, this has given you an idea of how we can avoid using partial fraction expansion. We avoid all those algebraic equations, and we can just sort of take our Laplace transform that we're given. We can compare it to the tables, and I know I pulled out the correct table entries, but we can compare it to the tables, and we can manipulate it algebraically to be in the correct form of the table. Now, I've tried to pick a problem that had a special case in the denominator where we needed to use completing the square, so you can get practice working on those completing the square problems. But hopefully this has given you some insight into how to do an inverse Laplace transform without partial fractions.